Hey, welcome back everyone. In this exercise, we are going to get a little more practice entering complex formulas in Excel. And we're going to name some cells to reinforce that concept a little more deeply. But most importantly, we are going to learn how to use the Excel if function, which is a really powerful tool that you'll end up using quite a bit as you run into more and more problems using Excel. And the use case for today's exercise is using Manning's equation to calculate how much water will flow in a circular channel. And to give you a little background into Manning's equation, I've prepared a few slides here. So Manning's equation is used to calculate how much water will flow in an open channel as a function of the width, the depth, the kind of the geometry of the channel, the material that's used to line that channel, and also the slope, how steep the channel is. This is something that's used quite frequently in engineering design. You can use it to estimate the flow through a natural channel, but it's probably more commonly used to calculate how much water will flow in a man-made channel, and also to make sure that those channels are designed properly with sufficient cross-section and slope and so forth to carry the design flow. And this is here are some other cases. You can use Manning's equation to calculate flow through a pipe. Typically it's used for pipes that are flowing partially full, such as a storm drain as shown in the lower right. But again, you can use it to calculate flow through just about anything. This is Manning's equation. It's kind of a semi-empirical equation. It's used to calculate Q, the flow rate, and that is either in meters cubed per second or feet cubed per second, depending on the units coefficient, which is U. You use 1 for metric or 1.49 for English units. N is the Manning friction factor, and that's shown there for a number of different common materials. And then the other coefficients are A, the cross-sectional area of flow. We'll describe that in the next few slides. RH is the hydraulic radius, which is the area divided by the wetted perimeter, which I'll show you how to calculate in a second. And S is the slope of the channel bottom. Now that's, for example, if you drop 1 meter every 100 meters, that would be a 1% slope, or 0.01. And the hydraulic radius is raised to the 2/3 power. The slope is raised to the 1/2 power. You take the square root of the slope. So you plug everything in, use consistent units, and based on the area and the hydraulic radius are a function of the geometry of the channel, and the slope is factored in, and the material, the friction factor. This friction factor basically accounts for how rough the surface is. Something with a high friction factor is going to have a little more shear stress on the edge. It's not going to flow as quickly, and something that's smoother will have a lower friction factor, resulting in a higher flow rate. So here's some different typical cross sections. This is a trapezoidal channel. With the trapezoidal channel, you'd have the bottom width is B, the slope is Z to 1, so a 2-to-1 slope would be 2 horizontal to 1 vertical. And if you do and then the depth is Y, so to get the cross-sectional area of flow, that's basically the cross-sectional area defined by the part of the cross-section that's water. So y times b plus y squared z would give you that. So y times b is this rectangular area in the section, and then y squared times z would be this 2 times this triangular part on the side. And then the wetted perimeter is the length along the perimeter of the channel that's wet. So in this case, it would be, from this dashed line, and for this geometry, that's b plus 2y times the square root of 1 plus z squared. If you do a rectangular channel, if you just make z equal to 0 and plug it in here, you get the equations for a rectangular channel. The area is y times b, and the wetted perimeter is b plus 2y. That's the simplest case of all these. And finally, this is the one we're going to do today, that if you have a circular channel, the calculations get a little bit more complicated. The cross-sectional area of flow is 1/8 alpha in radians minus sine alpha times d squared. The wetted perimeter, which again is this dashed line over here, is 1/2 alpha in radians times the diameter, or alpha times r times the radius is another way to express that. And but alpha, that angle alpha, it's kind of tricky to calculate that. If y is less than r, in other words, if the channel is less than half full, alpha is equal to pi minus 2 sine inverse r minus y over r. And if y is greater than r, alpha is equal to pi plus 2 sine inverse y minus r over r. And so this plus minus sign changes to a plus, and then instead of r minus y, we have y minus r. And so if we were to put this into a spreadsheet in Excel and do these calculations, we got to be careful, because the formula we use, the equation we use for alpha is going to depend on the input values of y with respect to r. So for that reason, we're going to need to use the if function so that we can plug in both equations and then use one based versus the other based on certain conditions. Also, something that needs to be noted is that we've got to make sure that y is never entered to a value that's larger than d or less than 0. Otherwise, these equations will blow up, and so we can use some data validation, input validation to make sure that's not going to be a problem. So let's go back to our spreadsheet here in Excel. We have the equations that we saw earlier that we're going to use now. So first of all, let's go up here, and the diameter is equal to 2 times the radius. So we're going to just enter that as a formula. So you can enter a radius, and that's automatically updated. Alpha, this angle in radians, is equal to, now let's do something else here. Let's enter some names for something. Oh, I take that back. These have already been named. So the radius is RAD. The diameter is D. The depth is Y. The roughness is N. The units are U. The slope is SO. And we have alpha, A for area, PW, RH, and Q. So pretty much they all follow this little thing in parentheses, although I guess here we should say that is R8D. And the reason we didn't use R for the name here is because, as we learned last time in one of our earlier videos, when you're naming cells, there are 2 names you can't use, and that's R or C. So we're going to use these names in our equation. So the area, the angle alpha is equal to 1/8 times open paren. Oh, excuse me, I'm doing the wrong equation. We're jumping right down to alpha. So we're going to jump right in and do this. I got my A terms confused. I was doing the area equation when I really should be doing the alpha equation. Sorry about that. So we're gonna immediately start out with our most complex equation here. So if y is less than r, we're going to use this formula. Otherwise, you're going to use that formula. So we're going to do that using an if function. So we're going to say equals if, open paren, logical test. So for this first argument, we need to put in a logical expression that's going to return true or false. And typically this is seeing if something is equal to, less than, greater than another value. And in this case, we're going to say y is less than RAD, the radius. Then the value if true, so we put a comma, and now we're going to put the expression if true. So y is less than radius. We're going to say alpha is equal to pi, we're going to use the pi function, minus 2 times sine inverse. Sine inverse is a sin. And that would be open paren, RAD minus y, close paren, slash RAD, close paren for the sine, and then we're going to do comma. And now we're going to do this second equation down here, because this is what happens if that condition is not true. And so we're going to do pi, open paren, close paren, the pi function, plus 2 times a sine, open paren, y minus RAD, close paren, slash RAD, close paren for the sine, close paren for the if function, enter, and there we go. Wow, that was a mouthful. So I'm going to click on that, and let's go up here and review this again. So right here we have our conditional expression, y less than RAD, and that refers to these two cells right here. So if y is less than RAD, then that is going to, then it will use the first or the second argument, which is basically this thing down here, pi minus 2 sine inverse RAD minus y over r, or RAD. And then if that's not true, it's going to use the second equation here, pi plus 2a sine y minus RAD over RAD. So again, the if function generally has 3 arguments, or it has 3 arguments. The first one is an expression that evaluates to true or false. If it evaluates to true, then it returns the value of the second argument, which is an expression. And if it's false, it returns the value of the third argument. And here we go. And that gave us 3.16, which is just larger than pi. But the depth that we have entered right here is 2.02. The radius is 2, so it's just barely above full. In which case the alpha should be just a little bit bigger than 180 degrees, or pi, which is correct. And so that seems to be entering the right set of values. And if we go let's go just below full, 1.98 or 1.9 or something like that. And once again, now it's just smaller than pi. So it looks like it's working out correctly. It switches between the two equations based on the relative values of y and r. So that's working. So now let's do our area. It's equal to 1 over 8 times alpha minus sine alpha times d squared, and we're using named cells, so this is all very easy to enter, and I made a mistake somewhere. What did I do wrong? Circular reference. Okay, so I need to say instead of a, I'm confusing those again just like I did a second ago. Instead of a, it's alpha. There we go, alpha and alpha. Okay, alpha, not a, referring to itself. So that works. Wetted perimeter equals 1/2 times alpha times d. Hydraulic radius is equal to the area divided by the wetted perimeter. And now we're ready to calculate Q. Q equals U/N times A times RH raised to the 2/3 power times SO raised to the 1/2 power. Now I put the powers of those two expressions in parentheses because if I didn't do that, it would take RH squared divided, and then take the result of that divided by 3, and that's not what we want. We want 2/3 to be evaluated first, and then RH to be raised to that power. So that's how we enter that, and now we have a correct value for Q, and away we go. Looks like it's calculating correctly. Now let me quickly show you another use of the if function. You'll notice that the units here, we have two options, 1.0 and 1.49. If we go down here somewhere, we can enter 1.0 and 1.49. So that's in A, 36 and 37. Now I'm going to go back here and I'm going to say, I'm going to go to the data menu and click on data validation and say we want the numbers to come from a list, and those numbers are in these two cells, and then we'll click OK. So now the user has to pick one of these two numbers, okay? And then what we want to do is we want to, so the units are either going to be feet squared per second, if it's English units, or if it's metric units, then it needs to be meters, and so forth. So we can use an if statement here to change those labels. So we'll say equals if u equals 1, then we want this to be a text constant that says meters. Otherwise, we want it to be feet. Okay, and I'm going to copy that down, and then I'm going to copy it right here, and I'm going to change that to meters squared and feet squared. And let's see, I'll copy this one and paste it here. I'm just doing Control-C, Control-V, copy, paste, and here we're going to say meters cubed per second and feet cubed per second. Alright, so now if we've done this correctly, if I change this back to meters, look what happens. Metric units, English units. See that? Now not just the value will change because of the U term here in the equation, but all these labels change, which is kind of nice. It shows you the correct units. And so there are a lot of really fun ways you can use the if function, and pretty simple really, just a condition and then you know, an expression if true and an expression if false, and you're off to the races. Before we leave this particular exercise, there's one more thing we want to do, and that is, you know, we use data validation to ensure that the user is only going to enter a 1 or a 1.49. There's another kind of data validation that comes in really useful here, and that is with respect to the depth y. When I was narrating over the slides in the introduction, I mentioned that you can't let the depth be larger than d or less than 0, because if you do, it blows up. So the depth is 4, so if I enter 5 for the, the diameter is 4. If I enter 5 for the depth, you'll see that we get a bunch of errors here. That's because it messes up this this sign inverse. And likewise, if I enter a negative depth, you get the same problem. And so now there are a couple ways to handle this. You can say, well, you know, hopefully the user's not an idiot and they're going to enter reasonable values. But another way to provide a little more guidance and make your workbook a little more rock solid is you can use input validation. And we've seen how to use that with a list, but you can use it for just single values as well. And so I'm going to go into the data validation menu after selecting the depth y, and I'm going to say allow a decimal number. Let's say we want it to be less than or equal to, let's say, no, between, that's what we want. So we want it to be between a minimum of 0 and a maximum of the diameter. So I'm just going to do equal B5. So yeah, we want to make sure it's between 0 and D, because anything else is going to give us a problem. And so we click OK. So now if I enter a value of 5, it says this value doesn't match the data validation restriction. So again, if I want to make that a little more helpful, I can say error, the depth y must be greater than 0 and less than the diameter d. Okay, now if I go to enter 5, I get an error message. And if I enter it negative, -5, same error message. And I'll keep getting that error message until I enter something correctly. Now again, if they enter something that's out of range, it's pretty obvious in this case what's wrong. But just in case, you know, there are a few times when this provides some nice helpful guidance to your users to put in values that don't blow things up.